Optical Transport Network (OTN) functional requirements. General. The fiber optic multiplexer system, OTN-based, shall be a high-capacity optical transmission system based on active OTN nodes linked by optical fibers, forming a reliable and redundant high-speed medium for the transparent transport of voice, data, Ethernet-based LAN, and video services. As the transmission system will be used as a backbone network, the system shall have the following characteristics: high availability, high reliability, dual ring configuration, easy to install and operate, scalable, high degree of flexibility with respect to the type of interfaces. The transmission system based on TDM, time division multiplexing, shall carry all channels for voice, data, LAN, and video communications within the same fibers, in order to guarantee independent and consistent communication between all interfaces. Each interface will be allocated a dedicated virtual channel with a minimum of overhead. The load on one channel shall not affect the load on another channel. As virtually all information is transmitted via the TDM system, the telecom system shall be implemented using two physically independent FO backbone cables supplied and installed by others. In case of a node failure, other nodes shall be able to find a backup path to this via this dual FO backbone network. TA OTN Network System Design Requirement Design. The dual telecom backbone FO cable shall connect each of the OTN nodes. The dual ring structure is required for redundancy purposes. In normal operation, only both rings shall carry the traffic, one in a clockwise direction and the other in a counterclockwise direction. The counterclockwise ring shall take over automatically with minimum delay whenever a problem occurs on the clockwise ring. If a cable break occurs on any individual FO cable, the system shall automatically perform a loopback operation by selecting the available FO path, clockwise or counterclockwise ring, isolating and reporting the fault, and maintaining communications of all user equipment connected to the network without any interruptions in traffic. In the event of a power failure, a ring reconfiguration, or when a new node is added to the ring, the complete network shall start up and reconfigure itself automatically. The network shall allow setting up point-to-point links between users, but also broadcast, multi-point, and multi-drop connections must be possible. Multi-point connections, or bus connections, allow any device to communicate with any other device connected to a common bus. Multi-drop connections allow a master device to send information to various slave devices. The slave stations can send something back on request of the master. The following OTN ring network functionality is required as a minimum. Dual ring operation is compulsory. The standby ring shall automatically take over whenever a fault occurs on the active ring. Moreover, the system must be able to create a ring structure in case of a cable break or a node failure loop-back operation. The maximum reconfiguration time in case of a node failure or cable break shall not exceed 150 milliseconds. A dual hot-swappable power supply with separate power cords is required. Any faulty interface card which is removed while the OTN is in service shall be hot pluggable, and the new card inserted shall be automatically configured and restored into service. Configuration data and specific software shall be stored locally in every OTN node to ensure an automatic and quick restart after a power outage. The database holding all relevant information on the system configuration shall be backed up in the OTN network management system. If configuration data is lost in a particular node, the OTN network management system must be able to restore the data. OTN system bandwidth. The OTN system bandwidth shall be calculated as per the requirements of various interfacing systems like SCADA, RTU, CCTV, FIDES, and PABX, which are using OTN system as the transmission system. The allocation of the bandwidth to the virtual channels shall be flexible and easy to perform via the OTN network management system. The bandwidth granularity shall be such that low-speed signals do not consume unnecessary bandwidth. The bandwidth allocation calculation needs to be submitted by the system integrator for review and approval. OTN system hardware requirements. General. The high-capacity OTN optical transmission system shall be the combination of a passive part, i.e. the optical fibers, and an active part, i.e. the OTN nodes. Each node shall be equipped with circuitry regenerating the optical signal, providing interfaces to the applications and monitoring and controlling the OTN node. The OTN node shall be of a modular design, allowing the installation of additional modules or the hot replacement of modules. The OTN node shall consist of a chassis, one or two hot swappable, redundant power supplies, slots for interface cards, and the system module and optical transceivers for the optical links. The slots shall allow a mix of interfaces to be installed, and all cards shall be front accessible. To enable traffic redirection in any direction for integrating with the existing rings at TRF and at KIDFA, the OTN node shall be appropriate logical routing cards, which shall redirect the traffic as configured from the OMS management systems. Node chassis. The chassis shall be industry standard 19-inch rack mount. All interface modules shall be easy to install. It shall be possible to insert and remove interface cards during system operation hot pluggable. The node chassis with all its interface cards and prefabricated cables shall be wired onto data access panels, MDF, etc. within the same cabinet. FO multiplexer interface cards. Every chassis shall be equipped with a primary FO multiplexer interface card that is responsible for the TDM multiplexing. The primary FO multiplexer interface card shall interface and transmit over the redundant FO backbone cable, control, monitor, and maintain the rings, and shall pass and receive status information from the other nodes. The internal logic and software will discover a fault in the rings and will cause the ring to reconfigure in the most optimal way. The FO multiplexer interface card shall have a display on the card showing the card status and the OTN node number as a minimum. Other diagnostic messages like faulty card, transmission errors, etc. shall also be displayed on the FO multiplexer card. The FO multiplexer interface card must be available in redundant configuration, and it shall be possible to hot plug these cards without affecting the network transmission or traffic. The optical transceivers shall interconnect the nodes using the two FO backbone cables. The transceivers shall support single-mode cables to ITU G652, 9125, and transmit at 1300 nanometers or 1550 nanometer wavelengths. Power supply cards. The node chassis shall be equipped with redundant power supply cards and shall operate on 24-volt DC solar-powered units at BVS stations and at 240 VAC at TRF and FRS. The power supply cards must be able to feed all interface cards. If one power supply in the redundant node chassis fails, the other power supply shall automatically take over, without interruption of transmission or interface card services. One of the power supplies, DC, can serve as a battery backup when connected to an external battery source. The OTN shall support fast Ethernet interface 100 megabits cards for transmission of signals related to SCADA, RTU, CCTV, and fence intrusion detection systems. Each interface card supporting a direct Ethernet connection shall provide at least 5 ports. It should be possible to assign each port to a separate independent Ethernet network. Each port shall support IEEE 802.3 compliant 10-base-T and IEEE 802.3U compliant 100-base-TX twisted pair interfaces with RJ45 connector. The ports shall support auto-sensing of 10-base-T versus 100-base-TX. At least one port shall support IEEE 802.3Z compliant 1000-base-T twisted pair interfaces with RJ45 connector. This port shall support auto-sensing of 10-base-T, 100-base-TX, and 1000-base-TX. Each port shall support 10 100 megapsec half-full duplex operation mode. The operation mode shall be selected via the auto-negotiation feature or manually via the OTN network management system. The interfaces must be fully transparent for all higher-level Ethernet protocols. The interfaces have to support port-based VLAN, IEEE 802.1Q, or must be VLAN transparent. Each port shall support at least 2 802.1P priority queues. The fiber optic transmission system shall support multiple independent Ethernet networks. The bandwidth per Ethernet network on the fiber optic transmission system is selectable from 1 Mbps to 180 Mbps. It shall be possible to use the Ethernet interface card in point-to-point or multi-point configurations. The Ethernet interface card shall support flow control according to IEEE 802.3x. The system should at least provide the following status information as a minimum: card active, inactive, card type, monitor selection, monitor active, data in input-output buffer, excessive collisions, packet too long, buffer status, packet removed, input buffer overflow. Voice interface cards. It shall be possible to transport 64 kbps analog signals between any 2 points in the transmission system. The 64 kbps interface shall be compliant with ITU-T recommendations G.703, codirectional, and G823. The interface card shall have 6 independent voice circuits.